Assalamualaikum and good day, dear students. Today we are going to continue with our discussion on the cooling load estimation analysis. This is the cooling load estimation table, and this will be the Appendix 1 heat load reference tables. I hope that you already familiarized with these two tools that we are going to use during our analysis on the cooling load estimation. Now let's have a look at the example for the cooling load estimation. This question states that a space is to be used for general office as an estimated 50 staffs shall be located at this office. Air conditioned for human comfort at 75 degrees Fahrenheit, 55% relative humidity, and 72 grain per pound. Estimate the peak cooling load requirement based on the following construction details. The information that is being given to us, the first one is the room size, 65 feet times 65 feet. This will represent the floor area, and we also have 10 feet for the ceiling height. The second item is the information about the wall, which is 4.5 inches brick wall with cement plaster on both sides. The information about the glass for each direction is also given, including the number of units, the size, the types, and the condition of that glass. The information about the door. So the types of the door for this case is glass, and we have the numbers of units involved for our buildings, and also stated here the direction where this door will be placed, and also given to us is the size for the doors. Well, for the roof, it is corrugated asbestos with suspended ceiling board, and the information for the lighting also has been given, which is 4 watts per square feet, and the type will be fluorescent. It is advisable to have a graphical representation such shown in this floor plan, so we can know where the location of the windows, where will be the location for the doors, and they are located at which cardinal direction. So another thing that will be important for you is, you know, the cardinal direction: north, south, east, and west. And please put the dimensions for the space. Right, so from the question we have all the informations where we can summarize all that informations as such, where the first thing is for the building, we can say it is a single story building, and of course for a single story building the location will be ground floor. As for the wall exposure, we don't have much information for the wall exposure to the sun. Therefore, for this particular question, we are going to assume that this building is going to be built at an open space. Therefore, all sides of the buildings will be exposed to the sun. For this general office building, we know that glass will be used for the door and also for the windows. Since this is a single-story building, therefore this building will have roofs. For the electrical and electronic equipment, since we don't know about this and it is not being given from the question, therefore there will be none. Alright, ladies and gentlemen, I would like to advise you to do this example together with me, so then maybe we can get more understanding and more insights on how to do the cooling load estimation analysis. First, let's fill up the general information about this building. So the space is used for general office, right? So for general office, the operation will be 12 hours per day. Then for the size, given from the question is the room size 65 feet times 65 feet, and if we calculate, we are going to get 4,225 square feet. So 4,225 square feet is representing the floor area for this general office. Next, we are going to multiply the floor area with the floor to ceiling height, and given to us is 10 feet. Therefore, we are going to get the value of 42,250 cubic feet. Now let's move to the psychometric analysis. If we look at the psychometric analysis, we have three conditions: the outside air, OA, the room condition, RM, and the difference between the outside air and also the room. Given to us from the question is the room condition, which is the dry bulb temperature 75 degrees Fahrenheit, the relative humidity 55%, and also the specific humidity in grain per pound 72. For the outside air condition, we can refer to the appendix 1 under the section design conditions. So as we can see, we have the values for the dry bulb temperature in degrees Fahrenheit, and we're going to take the value of 92 degrees Fahrenheit. For the relative humidity, we're going to take the value for the day, which is 60%, and as you can see, we don't have the information for the specific humidity. For your information, it is very important for us to have the value for the dry bulb temperature and the specific humidity. Therefore, please add to your appendix 1 for the design conditions. For the outside air, the specific humidity will be 136 grain per pound. Now we can feel the value for the outside air condition. Dry bulb will be 92. The relative humidity will be 60, and the specific humidity will be 136. Now we can determine the difference between the outside air condition and the room condition. For the dry bulb temperature, we are going to get the difference is 17 degrees Fahrenheit. For the relative humidity will be 5%. For the specific humidity, the difference will be 64 grain per pound. Now let's move to the other section, which is the ventilation. From the question, we know that the general office will have 50 staffs. This number of people will be multiplied with CFM per person that can be obtained from Appendix 1. From Table 11, the application will be General Office, and we are going to choose the recommended value for the CFM per person, and it will be 15 CFM per person. Square feet is the floor area that has been calculated previously. So the value for the floor area is 4,225 square feet. It's going to be multiplied with CFM per square feet that can be obtained from Appendix 1. From Table 1, we are going to take the application is office buildings. For the fresh air, we are going to take the average value. Therefore, the value is 0.25 CFM per square feet. For the third item, there are no exchange per hour given from the question. Therefore, we're going to use the value of 1, and the volume divided with 60 is equal to 704.17. Note that volume divided with 60 is this value, 42,250 divided with 60. Now we have completed the analysis for the ventilation section. So from these three, we can see that the value of 1056.25 CFM is the highest value. Therefore, we are going to take this value for our analysis later. Next will be the solar heat gain. As I mentioned to you, for the Table 7, the unit will be degree Fahrenheit. Right, first we are going to perform the analysis for the wall. In the summary for the information that we have for this building, I will state that we are going to assume this building is going to be built at an open space where all the wall side will be exposed to the sun. Any wall that exposed to the sun will be included to this section. But before that, we need to know the area of the wall. Please develop this table for each side. We are going to get the overall area. For example, we know that the ceiling to floor height is 10 feet, and we know the length and width is 65 feet each. So let's take the north side. So it's going to be this wall, right? So the total area for the north side will be 65 feet times 10 feet. So we're going to get 650 feet, right? And we have two doors located at the north side of the wall, and the size is 5 feet times 7 feet, and the number of units for the door will be 2. So for the glass area for the north side will be 5 feet times 7 feet, which gives us 35 feet, and we have two doors, therefore it's going to be 35 feet times 2, which gives us 70 feet. This represents the glass area for the north side. Now we are going to calculate the area for the wall only. So this will be the total area, and this will be the glass only area. Therefore, we are going to subtract 650 feet minus 70 feet, and we are going to get 580 feet. Now we can do for the rest of the side, east, south, and also west. So we are going to calculate the overall, the glass only, and the wall only area. And I also suggest you to total up the glass only area so then we can use this value later for the section B. And for the area for the roof, normally we are going to take is equal to the floor area. Now we are going to refer to table 7 for the temperature difference. As mentioned from the question, the material for the wall will be 4.5 inches brick wall that is approximately equal to 60 pounds per square feet of weight. Now we are going to refer to the 60 pounds per square feet, and the value will be taken for that respective sides of the wall that is exposed to the sun. So in our case we have north, east, south, and west. For the roof, actually we are going to refer to table 8. However, we don't have much information, so then we can select the specific width for that particular roof type. So we cannot use this table 8 in our analysis right now, but instead we are going to take the value of drive up temperature difference, which is 17 degrees Fahrenheit. Now we are going to refer to table 9 for the heat transfer coefficient. For the walls, we are going to take external walls, where the types is 4.5 inches brick wall with cement plaster on both sides. So the transmission coefficient U is equal to 0.48, and for the roof given to us, the type is corrugated asbestos sheets with suspended ceiling boards, and the value for the U is 0.28. Once we have all the values, we are going to determine the heat gain. Once we have determined the heat gain, we can move to the glass for the solar heat gain. And again, for the glass, it's going to be the glass sides that is exposed to the sun. In our case, north, east, south, and west. We are going to take the glass only area Next, we are going to refer to table 4. Normally, we are going to refer to the question for the design month. However, if it is not been given, normally we are going to choose the month of September and March. And for our case, we are going to choose the exposure sites will be north, east, south, and west, which is for the north will be 10, east 167, south 14, and west 167. Now we are going to refer to table 5 from the appendix 1. If we look at the information that has been given to us, the glass used for the windows are having internal blind, and the color also has been stated here. For east glass is medium color, for west glass is dark color, for south glass is medium color. The storage load in table 5 depends on the type of building. For normal brick building, the weight of the building is normally about 100 pound per square feet. For timber or lightweight buildings, the value is 30 pound per square feet, and for heavier brick buildings, the value will be 150 pound per square feet. For our case, the building used the normal brick, therefore the weight will be 100 pound per square feet. From table 5, we are going to refer to 12 hours of operation with internal shade, and the exposure will be east, south, west, north, and we are going to take the weight is equal to 100 pound per square feet. So for east, the value is 0.19, for south 0.51, west 0.72, and north 0.98. Now we are going to refer to table 6. We are going to choose the overall shade factor for each sides. So we are going to start with north. Since north we only have doors, so for doors there's nothing much that we have from the informations. Therefore we are going to choose type of glass regular plate 1/4 inches and no shades, so the value will be 0.19. 0.94. For east, we only have windows, and stated from the question is internal blind with medium color, so we are going to refer to the inside Venetian blind and medium color, so the value will be 0.65. For west, also we only have windows for the glass. It is internal blind dark color, so we are going to refer to the regular plate quarter inches, inside Venetian blind and dark color, so the value will be 0.74. While for south, we actually have doors and windows, therefore we are going to separate the south for doors and south for windows. So for doors, we are going to take the type of glass regular plate quarter inches and no shades, so the value will be 0.94. while for the windows, it is single regular plate quarter inches, then it has internal blind, so we are going to look at inside Venetian blind, and the color is medium, therefore the value will be 0.65. Now we are going to make adjustment to the solar heat gain for glass, since for south we have doors and windows, so we are going to separate the estimation for doors and windows. Now we are going to transfer all the values that we obtained from table 6. Once we have all the values for the heat gain for the section A solar heat gain, we can now calculate for the total A. The total A is equal to 57,895.21 BTU per hour. Now we can move to section B, transmission heat gain. The total glass area is 530 square feet, so we are going to put this value to the all glass area. Then we are going to refer to table 9. We are going to take the value of external walls, glass vertical, the value is 1.13, and the temperature difference is 17 degrees Fahrenheit, as been calculated previously in the psychometric analysis. For our case, we don't have any transmission heat gain through the wall, since it's already been catered by the solar heat gain. There is no partition to be considered, and for our building we only have roof which has been catered in solar heat gain. For the floor area is 4,225 square feet. Next, we are going to refer to table 9. For the floor, we are going to refer to the ceiling and floor, and we are going to take the value for the heat flow down, which is 0.22, and the temperature difference in degree Fahrenheit will be 17, and do not forget to minus with 2 degrees Fahrenheit. For the infiltration, in MEC351 we are not going to include infiltration in our estimation, but later we are going to take care of this infiltration inside our 10% safety factor. And now we can determine for the total B section. Now we are going to proceed to section C, internal heat. For the number of people, we know that for this general office, they're going to have 50 occupants. Next, we are going to refer to table 10. From table 10, we are going to take the typical Malaysia, and the applications will be offices, and we're going to look to the value of the sensible, which is 245 BTU per hour. Now for the lighting, the floor area is 4,225 square feet, and from table 1 we can obtain the value for watts per square feet. However, this value has been given from the question, which is 4 watts per square feet, and the type factor for the fluorescent light is 1.25, and we are going to multiply with the conversion, so then we can get in terms of BTU per hour. If the room is having equipments, then we can include in this section. However, for our example, there is no equipment involved. Now we can calculate the total for the C section. Now we can calculate the room sensible heat subtotal from section A, B, and section C. Once we obtain the room sensible heat subtotal, which is for our case 166,094.01 BTU per hour, we can now determine the safety factor of 10% for the room sensible heat subtotal. And now we can calculate the total room sensible heat RSH by adding these two values. For section D, outside sensible air, the item CFM is referring the ventilation, which we are going to take the maximum value from this analysis, which is 1056.25 CFM. For the bypass factor, we are going to refer to table 12. We are going to take the typical comfort application, and we are going to choose the value of 0.2, and the temperature difference from our psychometric analysis is 17 degrees Fahrenheit. Now we can calculate the total effective room sensible heat ERSH by adding these two values. Now we are going to move to section E, room latent heat. The number of people is 50%. Next, we are going to refer to table 10. Again, we are going to look at typical of Malaysia. Typical applications will be offices, and we are going to refer to the latent heat, and the value will be 205 BTU per hour. Since we don't have any equipments located at the general office, therefore the total E will be 10,250 BTU per hour, and we are going to calculate the safety factor 10% from the total E. The room latent heat RLH is the summation of total E and the item for the safety factor. For the outside air, the CFM will be 1056.25, which is the maximum CFM obtained from the ventilation analysis, and the specific humidity from the psychometric analysis is 64 grain per pound, and the bypass factor is the same value that has been chosen previously, which is 0.2, and we're going to multiply with the conversion factor 0.68. The total effective room latent heat ERLH is the summation of these two values, and the effective room total heat ERTH is the summation of total effective room sensible heat with total effective room latent heat. For the outside air heat analysis in section F, again the CFM for the sensible and latent is the maximum CFM from the ventilation analysis, which is given by 1056.25. The difference for the sensible will be the difference for the temperature, which is 17 degrees Fahrenheit, and for the latent will be the difference for the specific humidity given by 64 grain per pound, and for the bypass factor will be the same bypass factor that has been chosen previously, 0.2. For this analysis, we are going to minus 1 with the bypass factor, and we are going to multiply with the conversion for sensible and latent respectively. We can now obtain the total for the section F. Now we can obtain the grand total heat by adding these two values. The grand total heat for the general office, specifically for our example, is 259,518.724 BTU per hour. Do you get the same values with me?